Welcome to our webcast, Changing ROI for Industrial Robotics. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. Now I'm happy to introduce today's presenters. Jeff Fryman, Principal Consultant, JDF Consulting Enterprises Limited, is a retired U.S. Air Force officer. His 21-year career included 11 years as Program Manager overseeing technical training. He then spent 17 years as Director, Standards Development for Robotics Industry Association until retirement in 2013. RIA is North American trade group serving the robotics industry. At RIA, he was responsible for developing the 1999 and 2012 editions of the ANSI RIA R15.06 American National Standard for Industrial Robot Safety. He helped organize the annual National Robot Safety Conference, developed curricula for robot safety training, and taught hundreds of classes featuring the R15.06 methodology for conducting risk assessment. He was convener for the ISO International Standards Part 1 and 2 for Industrial Robot Safety from 2001 to 2014. Fryman is Vice Chair for the ANSI ASSE Standard for Control of Hazardous Energy, Lockout, Tagout, and Alternate Methods, and has been involved in other standards development on robotic and machine safety. Rick Vandenboom is Automated Systems Group Manager at Applied Manufacturing Technologies, AMT, a certified RIA integrator without a product or hardware agenda. He has more than 30 years of experience in the manufacturing automation industry with background including application engineering, sales, and operations management. He has worked for several international companies across multiple industries and has a track record of success in product development and new market introductions. I'm Mark Hosky, Webcast Moderator and Control Engineering Content Manager covering automation, controls, and instrumentation, including robotics, since 1994. And now, our first speaker, Jeff Fryman.
Hi there. Mark, it's a pleasure to be with you today, and I will be presenting on safety considerations for collaborative robot applications. Our learning objectives include learning what a robot called collaborative is all about and how to evaluate whether or not a process is appropriate for a collaborative robot, or is it an appropriate robot application. Collaborative robot operations. Collaborative is a special kind of operation between a person and a robot sharing a common workspace. This was not allowed under the 99 standard, but has been allowed by the introduction of our new ANSI RIA 1506 of 2012. This national adoption of an international standard, ISO 10218, introduces and allows collaborative robot applications. So what are we talking about? Well, collaborative operations have to be used for only predetermined tasks. They are possible when all required protective measures are active, and for robots which feature specifically designed collaboration content. The ISO 10218 Part 1, or Part 1 of the 1506, calls out several new technologies that are the motivators for allowing collaborative operation. Primary one is the concept of a safety-rated soft-axis space-limiting feature. This is where software defines the limit of the robot motion, and the space limit can be used to define any geometric shape. You can design inclusionary zones or exclusionary zones. You can determine where the robot is able to operate and where the human is able to safely operate around the robot. This and other features are only available on new robots, and they are optional features, and they must be requested when you purchase a robot. Each of our major manufacturers have a different name for this particular feature. You have to ask if your robot is equipped with this feature of safety-rated soft access and space limiting. The other enabling technologies are optional speed controls. This is where they are safety-rated. Specifically, use safety-rated reduced speed control. The safety rating meets the requirement of ISO standard 13849-1, specifically meeting a performance level equal to D and a structure category equal to 3. The speed of the tool center point, commonly called the TCP, does not exceed the limit set for reduced speed, and a protective stop is issued if a fault occurs. We also have optional speed controls where we have a safety-rated monitored speed, again providing monitoring meeting a performance level D, structure category 3. The speed of the tool center point or of an individual axis shall be monitored, and a protective stop issued if the selected speed is exceeded. And then we have safety-rated monitored stop, which is essentially a speed equal to 0. The robot is monitored and will not move in this stop position. We have identified several collaborative robot applications or methods of performing the application. And the robot system exhibits certain control performance in safety-rated monitored stop or hand guiding. These features are very similar to traditional applications, only we now allow the human to work directly with the robot. The safety requirements for these methods are well understood, and we are comfortable in the guidance that is provided for these methods. Two newer methods have been identified: speed and separation monitoring, power and force limiting by design or control. Neither of these is well understood. Speed and separation monitoring, well, we can do speed control. That's more or less a no-brainer. But the separation monitor, determining whether you're keeping a separation from a human or a separation from a moving machine like a forklift, we don't have that sensing capability. And the least understood of these is the power and force limiting either by design or control. We are introducing a new ISO technical specification, 15066, which will provide some additional information for collaborative applications. Risk assessment is a very key element of robot safety. Each and every robot system is unique. If you even look at the cookie-cutter welding applications, you are welding on different components. You must look at every system individually. And this is particularly the case when we're looking for power and force limited robots. We have to look for some additional issues, such as it's possible for non-hazardous processes only, no sharp edges. Special consideration has to be given to the gripper design. You don't want finger pinch points. You don't want sharp edges on the gripper. The ISO group is beginning a new work item on a technical report for grippers, specifically aimed at collaborative operations, and that will be available maybe by the end of the year. The direction of the robot movement versus the human location is also a significant issue. We have learned through our study of applications is that a collaborative operation is unsafe if the robot can strike the person above the neck. So the applications have to be designed where the motions of the robot are down and away from the individual and not up and toward the human, particularly toward a head angle. Your comprehensive risk assessment has to be a task-based risk assessment. You need to look carefully at your layout design, the limits of the robot system, hazard identification, task identification, and hazard elimination and risk reduction. All of these are important features when you're looking at risk assessment. There are a variety of task and hazard methodologies out there. The RIA has introduced a new technical report, TRR 15.306, which presents a known task-based risk assessment methodology suitable for robotics. It's revised but similar to the method that was offered in the 1999 edition of the 1506. Looking at the workspace requirements, your collaborative workspace shall be clearly defined. This is where the operator and the robot can directly interact. Throughout the standard, we've been careful not to tell you to paint the floor, but this may be an instance where we want to tell you to paint the floor so that the operator knows exactly where he's standing relative to where the robot motion may take place. You have to use a combination of safeguarding methods and protective devices to be in compliance with the robot performance features. Although we identify 4 specific methods of operation, we find in practice that there are combinations of them and not one true method as we describe them. If you have multiple people involved in an operation, each of them have to be protected with the necessary controls for a safe work environment. Your design of the workspace shall be such that the operator can easily perform all tasks. You want a clear area, you don't want a messy, obstructed area. There is a requirement for a minimum clearance of 500 millimeters from any trapping or pinch point. This is unique to collaborative robots. The change point between the autonomous and collaborative operations shall be designed so as not to endanger the personnel, and this goes to the layout of the cell. All of this must be carefully considered in your robot design. One or more of the safety features shall be selected to ensure a safe work environment for all of the personnel exposed to potential hazards. And any detected failure of the selected safety features shall result in a protective stop. An autonomous operation requires a deliberate restart outside the collaborative workspace. These requirements in the standard are directed toward the integrator and apply to how he should design his collaborative application. If we look at the individual operations we've identified, we have the safety-rated monitored stop. This is where the robot operates autonomously when no one's in the collaborative workspace. The robot stops motion if a person enters the collaborative workspace. A robot maintains a safety-rated monitored stop in order to allow direct interaction of an operator and the robot. We found in practice that this feature is included in combination with most of the applications. Another collaborative operation is hand guiding. A safety-rated monitor stop is issued when the robot reaches the handover position. The operator shall have a guiding device to move the robot to the intended position. The operator shall have clear visibility of the entire collaborative workspace. Again, very important. In collaborative operation, you want the operator to be able to see what's going on in the entire area. And when the guiding device is released, a safety-rated monitored stop is issued. The third, speed and separation monitoring, is relatively new. The system is designed to maintain a safe separation between the operator and the robot in a dynamic manner. I sometimes call this dancing with the robot. If you're dancing with a forklift, well, we probably don't care. But if the robot is dancing with a human, we care. But that's where we don't have the sensing capabilities. We have several organizations, both in the U.S. and Europe, looking into sensor technology to see if they can improve on the ability to detect the difference between a human and an inanimate object in the workspace. You use the risk assessment to determine what the minimum separation distance should be. And then finally, our power and force limiting by design or control. This is where the robot can interface directly with a person, can touch a person. I would say strike a person, but I don't want to give that impression. To a point where the human will not be injured. The robot cannot apply enough power or force and hurt the human. This originally was going to be direction to the robot manufacturers, kind of turning the big bad 6-axis articulated robots into WIMPs. However, we found that was impractical. If you made them weak enough that they couldn't hurt a human, they also weren't strong enough to perform any work. So, the direction we give now is to the integrator in his design of the collaborative robot, where the robot, when it is free to strike someone, will not strike them with sufficient force to cause harm, but when it's ready to do the work, it has enough power to do the work. Hence our discussion about grippers and the fact that you don't want finger pinch points with a gripper. The new ISO Technical Specification 15066 will contain additional information and guidance on collaborative robot application. I just returned from our most recent meeting in Japan, where we approved the publication of the document. It has now been forwarded to the ISO Central Secretariat in Geneva, Switzerland, for their production and publication of the document. I have been promising this document for months and months. It is now only a matter of months away, but it is totally out of our hands, and we do not know how long it will take for the published document to be available to the public. Biggest item you're going to find in this new technical specification is the results of a study that we commissioned with the University of Mainz in Germany. And that study was basically the onset of pain. We have lots of data, particularly from the auto industry, telling us how much pressure will break a bone, how much pressure will cut the skin. But these are injuries, and we cannot allow injuries. When we write a standard that says it is okay to work with a machine, that means that the worker comes to work in a healthy condition, he goes home in a healthy condition. We can't expose him to a hazard of being injured. So the approach we're taking is maximum injury at a failure would be a bruise or a contusion. So this study, using a probe and test subjects, when did a pressure applied to the body turn into pain? And there were 29 pressure points that we had on the body, so we have a lot of test results on that. Anything above the neck is basically dangerous. Anything below the neck, we can assign some numbers to. Now, these numbers that I have on this slide is preliminary. This is not the final report. But we looked at two types of pressures, one quasi-static and one transit. Quasi-static is a pinching situation. This is where you've been caught in a clamp or the robot is pushing against you and your body part cannot move. It's kind of a trapping situation. And then the transit control is a transit strike where the body is not constrained. So we are commissioning another study, again in Germany with the Fraunhofer Institute in Mecklenburg. And this is going to be to give us some finite numbers relative to transient. Right now, we are using a multiplier of 2 to the pressure that we determined was the onset of pain. So, with this information, we hope to have very successful collaborative robot applications in the future. I thank you again for your attention. This is my contact information. I work through the Robotic Industries Association, and I do training for them. Mark, thank you.
Great. Thanks very much, Jeff. And now on to Rick Vandenboom, AMT. Rick?
Thanks, Mark. For my part of the webcast, we'll look at the mechanics and economics of robotic automation, including collaborative robots. We start by breaking down the approach into 4 key areas set up in logical order that we need to know and consider when approaching robotic automation. And this includes collaborative robots. When we look at collaborative robots, it's really no different than traditional robotic automation in terms of the steps that we go through. We'll look at the top reasons for automating, break down the top business requirements taken into consideration, and we'll review what's important about your process. The combination of good reason, business requirements tied to metrics, and process complexity will dictate the appropriate levels of robotic automation that's required, and more importantly, can be supported by your facility and your organizational talent. Let's touch on a few of the economic drivers for automation. There's technology improvements. In the area of robotics, the manufacturers keep adding more intelligence and capability, and the emergence of collaborative robots is a great example of that. There's new market segments with proven applications. One area that we've seen a big surge recently is in aerospace, where they've been leveraging a lot of techniques that have been used and automation that's been used in the automotive industry to automate the building of airplanes. There's the reshoring growth, companies moving their operations back to North America and to the U.S. to have better control over quality of products. There's the expansion where there's continuous need to manufacture new energy-efficient materials. Global competition forces higher quality and increased utilization of plants. Consumer markets continue to grow, and product life cycles continue to shrink. And certainly the quality of work while removing humans from unsafe applications are becoming must-do tasks for many of the companies. So the first question you should ask yourselves is, should we automate? You know, we all know that robots are pretty cool, and there's thousands of applications of automated systems around the world working day in and day out. The emergence of collaborative robots starts to open even more possibilities. So you think everybody should use robots and start to automate. And really the question is, should they? I mean, the truth is not every process is a good candidate for robotic automation or even collaborative robots. There's a lot of good reasons why we should automate, such as safety, cost, ergonomics, quality, and certainly throughput. You need an automation approach to answer the single most important question first, and that is, should you automate? This is where you need to look at your organization, the talent within your organization, and have frank and unbiased input in terms of your automation initiative. So where do we start? In many industries such as automotive, they have years of experience in automation. They have the benefit of dedicated teams of people who really help make these decisions and evaluate the process, down to what type of clamp they use on an end effector. As automation and industrial robots shift into new industries and applications and less mature processes, there's a lot more education that needs to take place, and we find this to be especially true with the introduction of collaborative robots. With the introduction of collaborative robots, there are many companies looking to automate that have never done any type of automation in their plants before. So why do we automate? Because we want to increase throughput, quality, and safety, and at the same time we want to reduce our labor costs and our manufacturing footprint. We want to produce more with less people and a smaller footprint while increasing our efficiency. So the difficult part really is tying business reasons to the projects and understanding how to quantify the project and the return on investment. Once we've identified the top reasons and business requirements for a project, we also need to understand the system attributes and which ones are important to us on our manufacturing floor and for our particular organization. So let's touch on some of the top reasons that we should automate. There's improved throughput. We know robots can move a lot faster than people, but do you really have the demand for that higher throughput? If we make more, is somebody going to buy that from us? So you need to understand the current baseline of your process. If there's upstream and downstream processes that are bottlenecking the operations. So we need to focus on optimizing where you need to be, looking at material flows, buffer sizes, station utilization, throughput, so on and so forth. Another reason that we hear all the time is we want to reduce direct labor costs. So we know that machines can replace direct labor, but sometimes it has other implications in our manufacturing process. So you need to make sure that you're considering all of these costs. Sometimes we add automation, but it requires us to hire additional engineers, technologists, maintenance people to support and operate the equipment. We also need to make sure we understand all of the operators' operations on the plant floor so that as we implement the automation, we're having it do a one-for-one replacement of those tasks. Another reason for automating is to improve quality. Are your parts and components going to achieve the same level of quality when you automate? And then how are you going to check them to make sure that you are, in fact, meeting those quality requirements? So improving safety is a big factor for automation, and Jeff talked a lot about the requirements for that. Safety, as we look at developing systems for customers, is always a big consideration, whether it's with traditional industrial robots or the introduction of collaborative robots in the manufacturing space. So robots can perform a lot of dangerous tasks, ergonomically challenging tasks, but we always have to quantify the cost benefit of the required safety improvements to warrant the actual project. The introduction of collaborative robots, it opens a lot of new possibilities for new applications, but I can't stress enough that we need to focus on the fundamental safety concerns for automation, even when employing the collaborative robots. Another consideration for automating is footprint. How can we do more with the floor space that we have available? As we look at automation projects, sometimes this can be a little bit misleading. There are cases by putting automated systems in that you reduce the footprint, but there are other implications where perhaps you have to grow the area for safety fencing, for staging material, for delivery, and things of that nature. We talked about some of the reasons for automating. Just to touch on a few of what we consider to be the bad reasons. First is trade shows. I can't tell you how many times I've gone to a plant and the engineer says, my boss just got back from a trade show and he saw these new collaborative robots and told me to get one in here. So the motivation is, the new shiny object as opposed to let's go out and figure out where we can employ automation to really solve a problem for us. Another reason is they hear their competition is automating and really don't understand why that competitor is automating, if they truly justify that or if they're trying to solve a problem. And then this time of year, the end of the year, very often there's capital budget available. It's the end of the year, there's money out there, and somebody says, hey, go out and spend this money or we're going to lose it. So they go out and make a big push for an automated system without having really thought through how that will be used in the plant and justifying that purchase. Let's move on. We'll talk a little bit about business requirements of the projects with any typical automation project. First, we have schedule requirements. We need to know, can we meet the production milestones and part volumes to match our startup dates that we have? We all want the shortest schedule, the highest quality, and the lowest cost. It's very difficult to do all three, so pick two and focus on those is our recommendation. There's lead times to be considered. Many times the lead time of a single major component in the system is going to drive your overall schedule, regardless of what your scheduling requirements are. Make sure you understand what those are before setting up the overall schedule for your project. And there's certainly a capital budget limits. So you really need to have very open and frank discussion within the organization. Understand what your budget limitations are, what the ROI metrics are, and understand what happens if you go over budget. Are there additional funds available, and how is that going to be received by the organization? Next are the ROI requirements. This is an area that you really need to spend some time and understand from the management of the company through the financial areas. What are the requirements for ROI? Have it clearly defined, understand what your payback periods are, your primary goals. You can start by establishing some of the assumptions of how many shifts you're going to work, how much it costs per year for each of the operators, and so on. Consider all of the costs by defining the labor trade-offs, some of the facility changes, and everything else that you need for a successful automation project. Once you've done that, you can calculate the available dollars you have to spend on the project and make sure that your expectations fall within your budget constraints. So let's move on to your process. It's always surprising to me how many companies don't really have a good handle on their manufacturing process. You go out on the floor, you start talking to operators and looking at posted standard operating procedures and find out that there's a big disconnect. So it's important to really do a good analysis of the information and the operations on the floor and make sure that's getting back to the team that's defining the automation project. Make sure you're not missing any important steps in the manufacturing process. So what's important about your process? Really you have to start with the product mix that you have. How many components go into making a product, the complexity of that, and how well you can automate it. Sorry, I missed the slide here. The other thing that we need to consider is the number of operators. It's important to know what effect automating is going to have on the current operators on the shop floor, whether they're interacting with the automation, if they're being displaced by the automation, and what effect that has on production, as well as the personnel that are left on the shop floor producing the product. What type of equipment do you have now? You may have a sophisticated machining line with machining centers that are being loaded and unloaded by operators. If we look at loading the machines with the robot, we also have to look at how is the part being presented to the robot. what type of dunnage is going to be required to position those parts for robotic interfacing. Where will it be? How are parts oriented? What type of tolerances do we have to deal with? We might even get into the point of needing additional vision systems to help guide the robots. So you need to really take a good look at what you have today and what you anticipate that process to look like. Cycle time. We need to understand what our current cycle times are, and that helps us estimate the feasibility for future requirements and allows us to better understand current variation, and that could be a very powerful tool for us. And then there's system throughput. We need to know what the current throughput is, what the anticipated throughput is by employing the automation. But it's also very important to understand bottlenecks in the current operation and what impact those are going to have by automating. You need to really understand all these variables that drive the variation and downtime in the system as well. And there's quality. We need to understand, even if it's not our primary motivation in automating, to improve quality, we certainly need to understand the impact of the automation on quality of the product. Need to set some targets for that, some expectation, what type of variation is permissible, what type of scrap and rework you're expecting. So it's important to consider that and include that in part of any automated system in terms of specifying those requirements. And again, there's the footprint. We need to have a handle on what are the trade-offs between automating operations and the plant floor space, whether it's going to take more space, less space, the considerations for material flow, dunnage, so on and so forth. Now it's important that we talk about the appropriate level of automation. Many types of applications have been automated for many years. The bugs have been worked out, and there's really off-the-shelf solutions that are readily available from a variety of different suppliers. In these cases, you can find suppliers that specialize in a solution and get very competitive offerings. I think Jeff may have mentioned welding earlier. There's certain welding applications that are very sophisticated but very well developed. So leverage the expertise that's out in the industry and don't go out and try to reinvent the wheel for sure. Now the introduction of collaborative robots, it really starts to open up a lot of new possibilities to rethink current operations, expand levels of automation, and approach new projects that you may not have considered because of the sophistication and safety considerations with traditional industrial robots. So automation is a long-term investment, and based on it, we've answered some of the questions, including process, assemblies, and part volumes. It's going to determine the required level of automation and the types of robots that you might use. If you're in a process that is high speed, high volume, precision tolerances, and low product mix, you may be looking at fixed automation or maybe traditional industrial robots. In many cases, we find automated lines have a mix of both of those. How are you going to move product around the plant or within the system? You're going to be looking at your footprint, the material flow for incoming material, work in process, outbound product. You might have a small footprint and a small budget, and conveyors will likely be a better option for you than AGVs for moving material around, for example. Inspections can be pretty difficult to automate. Quantitative inspections certainly lend themselves to automation more than qualitative. But in any case, you really want to quantify the inspection process, know what the specs are, and what level of automation you need for that inspection with these robotic systems. And after reviewing the level of robotic automation that's appropriate, you really need to decide whether you as a company, if you're ready to self-integrate, or if you'll go outside to an integrator or an automation partner. You need to consider the capabilities, time and resources, your application experience, and safety design liabilities. You know, the best automation solution should always embrace and make use of your in-house expertise and not ignore or replace, what you have in-house. You know, certainly nobody knows your process better than you do. So, you know, when you're going outside seeking automation help, we certainly recommend that you find a company that appreciates and respects your in-house knowledge. It really wants you to be a part of whatever solution that we put together. If you do decide to go outside for automation help, look for an integrator that has your best interest in mind, not one that's simply pushing up, a product or a solution that might not suit your specific needs. Find a partner who's going to work alongside of you, lead when expected, but always lets the facts speak for themselves in terms of driving the automation solution for your company. So there are multiple ways to solve most manufacturing problems, but there's only one best way to solve a problem, although we find there are many acceptable ways to solve the same problem. When it comes to making your final decision, the options you consider should be the result of a structured, empirical approach that's removed the guesswork out of what you can expect from your automation project. So conceiving, designing, and implementing custom automation or robotic solutions, it's a science. Requires skill level and a multitude of disciplines. So it begins with gathering the right data, following a structured analysis, and presenting multiple fact-based solutions before making your decision. So set targets for your automation and take into consideration the system attributes, the metrics, and if you have an existing system, use that as a baseline for establishing these new targets. So now if we made it this far through the analysis and definition of an automation project, we're assuming you have a good team, correct team in place with the right talent. You want to take it to the next level and really get into more engineered ideas. So at this point, you develop relevant simulation concepts based on actual sequences, throughput, and floor space, put together a functional spec, layouts, cost estimates, and you're on your way to defining and implementing a correctly engineered robotic solution for your company. So with that, I thank you for your time and attention. You'll see my contact information here if you have any further questions. At AMT, we're an automation engineering services and system integration company. And we offer a wide range of engineering services that support factory automation, as well as full turnkey automation design and build. So thanks again, and back to you, Mark.
Hey, thanks very much, Rick. A lot of good information there. I appreciate it. Now we'll have a question and answer session. The audience listening live can type questions for today's presenter in the Ask a Question box on the screen. I see a number of questions already. We'll answer as many questions as we can until the top of the hour. Within a few days, the presentation will be available for on-demand viewing along with a link to the quiz for potential PDH credit. We'll post the archive on Control Engineering's website, and we'll send you an email message with the link connecting directly to it and related resources after it's ready. If you contact any speakers here directly via email, please reference the webcast in the subject line to help ensure that we recognize the email in the correct context. And now on to the questions. What technical resources are necessary to apply robotic elements in an application?
Sure, I can address that. typically there's going to be multiple disciplines in designing and implementing a robotic solution that starts with simulation, mechanical design, there's electrical elements, as well as the robot programming itself. So we really look at those four primary automation engineering disciplines.
Thanks, Rick. How can the flexibility of a robot be factored into ROI?
So I think the way that you can factor that in is really looking at the number of operations that a robot is able to do. That could be through the use of a single tool, employing things such as automatic tool changers that allows a robot to perform multiple tasks and not be single-purposed.
Good. Here's one for you, Jeff. Can robotics be controlled wirelessly in a safe and controlled manner?
Well, obviously depends upon the implementation, but the standard does provide for wireless pendants, and it talks about how the mechanics of that have to be employed. So I have seen one recent example. It's been allowed for a number of years, but it's just now beginning to get some traction.
And certainly in other industries, wireless moves multi-ton cranes in some applications as well.
Same principle.
Yeah, yeah. So the robot stop points can be both manual and controlled by the operator and automatic? Maybe Jeff?
Yeah, maybe I should explain. Collaborative robot applications are in automatic. The robot is always in automatic. The application programs what the robot's response to a human is going to be.
Good. And then can robots be used in job shops where there are a multitude of products being developed for different customers?
Absolutely. In fact, we see the collaborative robots fitting very well into that space where they can be moved, they become portable, if you will, in certain applications, moving from one operation to another. And with the hand-guided teaching for simple operations, the robots can, again, perform multiple tasks for multiple, on multiple lines, if you will.
Good, thank you. Here's someone who's met Jeff a lot of times at various robotic conferences. He wants to know more about ISO TC 184 SC2 committee outcomes. Do you have any updates?
Well, actually, I have an important update. Effective the first of the year, the SC2 becomes TC 299. We now have our own technical committee and higher visibility within the ISO community. The working groups will continue the same. I suspect the ISO 10218 will come up for periodic review here in another year or so. The committee is continuing to work on the activities. We're just finished with the collaborative robot. Now we're going to do manual load station technical report and collaborative robot gripper technical report. So our activities continue.
Good. And with the speed and separation monitoring and power and force limiting, what do manufacturers provide in terms of supporting documentation to meet the PLD Cat 3 requirements?
Well, obviously that's going to vary between manufacturer and what they do. The ISO and 1506 standards call out what documentation they do have to provide, and the certification to a performance level D structure 3 or whatever performance level and structure category they like is generally a self-certification, but can sometimes be certified too by TUV and other notified bodies.
So the robot manufacturers are learning too, and the documentation is generally improving?
Yes, indeed. It is a moving target, and it's improving daily.
Great, thanks. Any thoughts on quality control at plants that use robotics?
Yes, I think if I understand the question correctly, is really utilizing robots as part of the quality control process. And there are a number of applications that we've helped inspection companies with, where we've taken inspection technology, put it on the robots, and we're able to employ that as part of their quality control strategies in the plant. Whether it was doing dimensional checks, or really replacing repetitive actions that are done by operators. Some of the new quality-based systems, a lot of these are vision-based systems, are able to actually inspect a wide variety of products. There's a lot of flexibility because you don't have hard tooling associated with those operations. So I think that's the trend over the last 5 to 10 years is really moving a lot of traditional quality control operations that have been offline into a robotic inline environment.
Great, thanks, Rick. Thanks to the audience, too, for the great questions. We're going to try to get to as many of these unanswered questions as we can offline with the connected resources with the archive version. Thanks again to Jeff Fryman and Rick Vanden Boom for sharing their time and expertise, and thanks to RIA for help in securing the speakers for this webcast.